Okay, with that brief introduction, I'm Alexander, and this is Scary Stuff Less Metaprogramming, or rather a showcase of doing metaprogramming without macros in Scala tree. So let's get right into it. About me, I've been a Scala developer for the past 3 years now, and I'm also the creator and maintainer of Ducktape, a small Scala library that does data transformations and a lot of macros as well. And now for the talk itself, it's based on a blog post I created 2 years ago. It's called Inline Your Boilerplate. It more or less touches upon the same topics as we'll be discussing today. So basically doing a lot of macro stuff without doing macros, right? Macros bad is the tagline of this talk. Not actually, I'm just joking, but you know. So yeah, the problem with this blog post is it was published 2 years ago, right? So there's a lot of stuff that has happened during that time and now. The most significant one of which is, I think, the specification of match types. Once that got specified, all of the match type tricks that I used there do not work anymore. So yeah, think about this talk as like a refreshed version of this. And now onto the agenda itself. So there's only 2 points there. So we'll have a quick walkthrough of the stuff we will be using, the stuff we won't be using, right? And then we go to the live coding session, where we'll be implementing like a small library that does case class transformations in 3 steps. I'm going to show you. So yeah, that's it. Let's begin. So to start with, there's I call it the iceberg, but it's an upside down iceberg. Actually, that's not how an iceberg looks like, right? So the iceberg of complexity, there's 2 layers to that. So the tip, the shallow depths, and the abyss. So the tip is the stuff we'll be looking at today. So basically everything that doesn't touch macros but still compile timey. Shallow depths is what I call lightweight macros. So macros that only operate on expressions and quoted code. And then the abyss is where you do AST stuff, right? The most fun part of that. So yeah, let's go to the stuff at the top. So literal types, the Scala compile time package, mirrors, match types, and selectable and named tuples. So first one of which is literal types. As the name implies, each literal in Scala has its literal type reflected here, which means that we can have a string that says I'm a literal type, and it will actually have a type of I'm a literal type, right? And that's supported for all of the primitives per string. We'll be using that actually that actually gets used to encode information about case classes. But we'll be using that as well as a way of basically passing information in our type level computations. One more thing to mention here is that there is a bridge where we can basically get a runtime value of that literal type. It's called value of. It's a special case type class that gets generated by the compiler that materializes a given literal type into its runtime counterpart, right? So that's it for literal types. Now let's move on to match types. So match types are basically type level functions. They take in parameters just as functions. They take parameters as types, and they spit out other types as results. So for example, here we have a match type that takes A and B, both of which are types in our tuple. It first zips them together here, and then maps over the zipped together tuple by wrapping in an option. So if you squint hard enough, that's basically just method calls, but with types, right? So if we were to invoke that with those 2 tuples, so int string and double, and the one in reverse, the result will be this. So you can see that this got paired together, right? This, and this, and then all of them got wrapped in an option here. And there's one more cool thing about the Scala tree standard library, because it provides a bunch of match types that work with tuples, because tuples are now encoded as H-lists, right? So you can really think about a tuple in Scala tree as like a collection. So you can map over a tuple, you can flat map over a tuple, you can reduce a tuple, you can fold over a tuple, you can do whatever. And yeah, as I said, the tuple companion object provides like a collections library for tuples, which will come very handy for us. And apart from that, nothing stops us from having our own match types. They can be recursive, they can be whatever. We can do a tic-tac-toe with match types, probably, I don't know. So yeah. And then moving on to the Scala compiler package, a very small subset of it though. So we will, which is basically, so the Scala compiler package is basically a set of compiler special case methods tailored specifically for doing like type level stuff. Like for example here, SummonAll, right? You fit, so SummonAll takes in a tuple of type classes and then it materializes the tuple for you to use later on. Like I do here, so I take 3 literal strings, I map them over with value of, so that basically becomes a tuple of value of those strings. Materialize that by SummonAll, that compiles. If it doesn't compile, that means there is no instance of that in the implicit scope. And I use it at runtime, right, to get the values back. There's also a shortened version of that called const value tuple, which basically does the same thing, but it's shorter. You just feed it a bunch of literal types, and that get materialized for you, just like that. Now, as I said, there's much more to this, but we only be using those 2 things here. So yeah, moving on to the mirrors. So a mirror is a way of representing either a case class or an enum, but we'll be only looking at case classes today. So I'm just gonna show an example for a case class. So a mirror gives you information about that case class. It gives you its name, it gives you its fields, it fields labels, and probably some other stuff. And it's actually, if you could look at here, it's encoded as types in the mirror. That's because that information needs to be encoded as a type because we want to use that at the type level, or rather at compile time, right? So if you look at here, the types are encoded as just a tuple of types, whatever. The labels are actually encoded as a tuple of literal strings. And yeah, that's how they get represented, and that's how we basically will use them. And now for case classes in particular, there's also a from product method that gets generated that you can fit any product into, which means that it's not very safe at runtime. But you can feed it any product. It will try to feed that into the constructor of a case class that's being reflected here, right? So for example, if I feed it 1 string and a list of something, I get back an example like that. So yeah, that's mirrors. Moving on to the selectable and named tuples. So named tuples are a new feature that's being standardized in Scala 3.6.2, not 0.0, don't ask about 0.0. And yeah, it's basically tuples but with names, right? So the syntax looks like that. You specify the names, you specify the types, you initialize it like that. And yeah, you can just refer to those fields by doing, for example, .in, just like you would do in a case class. Of course, you cannot have like made-up names that won't compile anymore. And what's actually pretty fun about them is the new interaction with selectable. So selectable now supports something called the type of fields, which we need to feed it a named tuple. And how it works is then the selectable instance will actually copy over those fields to the selectable itself, if that makes sense, so that they can get used with select dynamic here. That of course will fail at runtime here, but that's just an example. So if I call selector.int, that will actually not compile and work. And if I call selector.madeUp thing, that will not compile. And the name of the field gets reflected into here, and you can do a lot of fun stuff with that. And yeah, and one more thing about selectable is it's the only, I think this is the only way of introducing new fields and definitions to like macro generated or not very macro generated stuff, because Scala 3 macros cannot generate new definitions, right? Bar from selectable. Yeah, and now for the stuff that we won't be using, just a quick run through. So the shallow depths, so lightweight macros, that's how in my mind, a lightweight macro looks like. Basically a bunch of code that only matches on, for example, types, and uses like the higher level methods on that. This actually just materializes a bunch of literal strings into their runtime counterparts. And yeah, just like that. And then for just to show the same version of that, but with ASTs, so the abyss. yeah, so that basically what I mean by that is working on ASTs directly. So instead of doing like a cool pattern match like here, that's more or less type safe, I do this stuff, which might break probably if you feed it a tuple that's not literally the same, but more or less works. It's more verbose, and it's more like you need to watch out of it. But don't worry about it, we won't be using that today. And that's because we will be now building that small library I talked about, so transforming between case classes in 3 steps. So first one will be the basic step where we transform between case classes that have more fields into a case classes that has less fields, or maybe they have the same amount of fields. But the crux of that is the field names and the field types under those fields just need to fit, right? And then we've got the intermediate level, which will be actually doing pretty much the same thing as here. So the fields still need to match, but the types that correspond to those fields can be different because we'll be materializing a typeclass instance. And then for the last trick here will be the fancy transformations, where we be able to fill in the blanks of like failed transformations or overwrite other ones, right? So let me step over that cable first because I'm probably gonna trip up and oops, and mess up my stand made of coffee. Yeah. Okay. So yeah, let's get right into it. So the basic example is we have 2 case classes. One's called album, the other is called ever so slightly more detailed album, and that's because the detailed album has one additional field here. And what I want the end product to look like and work like is you just get a detailed album, you call convert to album, and that works. But doing that the other way around, right? That should fail at compile time because you cannot really build a detailed album out of our album because there's no field correspondence for all of the fields. So yeah, so to do that, we just need to check if the source has a subset of destinations fields. And to do that, I'm gonna jump to my IDE now and probably break. Oh, that's not my IDE. Where's the IDE? Come on. Okay, so first of all, is this sort of readable? Can I make it a little bit smaller? Okay, a little bit smaller. Is this readable?
Yeah.
Cool. Okay, nice. So where was I? Live, basic. Okay. So what we have here, can I make it? Yeah, that's even nicer. So what I have here is basically the same example as we saw on the slide, right? So an album, an ever so slightly more detailed album, whatever, and some tests that we want for them to actually pass. But yeah, let's first think about how we wanna approach this. So first of all, I'm gonna declare a small class called a field, right? Because we need to somehow represent a field. I'm going to represent it as that. It's not going to have any runtime information because it's only going to be used at compile time. So it's made of a name of the field and the type of the field, right? Where the name needs to be a literal string. So I make it a subtype of string. So yeah, and now for how we actually build, how do you actually get fields out of a case class, right? So to do that, we will need a match type of all things. Object field, let's call it, whoops. Yeah, okay. Let's call it off. And it's gonna take labels as a tuple. I'm struggling here a bit. And types, which is also a tuple. Right, yeah. And what we're gonna do with that is first of all we need to zip those together. So tuple.zip, uppercase, yeah, labels, types, good. Okay, now we actually find ourselves with a tuple of like field names and the field types. But that's not the whole story yet, because we need to map over it. Boom, like that. Yeah, map over it. And now my lambda is here. That's cool. And so, because I know this actually makes a tuple, right? So I can unpack that by using match, another match type, but as I think an anonymous one. So I say that if it's a tuple of label and type, construct a field for me with label, label and type. That should work. Awesome. Yeah. So now what I'm finding myself with is actually a tuple of fields, so encoded like that, as opposed to being just a tuple of pairs, basically. Okay. So now we know more or less how to build out fields, but we still need to check. We still need to know how do we check the if the source type has a superset of the destination type, right? So to do that, I'm going to employ another party trick. But let's first look at, let's get name, or maybe not, field 1 and int. I'm going to use the intersection here. Field 2 and string, right? And now for my destination type, we're going to use field, let's go with field 1 for now. Maybe field 2. Field 2, and it's a string as well. Right? So because I'm using intersections, the type checker will actually be able to tell me if source is a subtype of destination, right? Yeah, it compiled, so it is a subtype of destination. And that's because all of the fields, that's because source has this inside of it, right? So if I change even so slightly to that, that should start compiling. Yeah, cool. So basically what we need to do is we need to go from our labels, for a tuple of fields, we need to go into an intersection of those fields. And a way of doing that is just another match type. So A, whoops, and B, which is a tuple, right? Yeah, cool. And to do that, we just fold over a tuple. So tuple.fold, we fold, actually that's just, just need this one. We fold over a tuple like that. So A is the tuple we are folding on. Z, the type Z, will be our 0. So for intersection types, it's any. And then the accumulator and the current value. So we just call it cur ACC. Use a type lambda and just do current.acc, right? And that should give us an intersection of the tuple. And now on to actually making the conversion work. So first of all, we don't want cases where not all of the fields are reflected in the source to compile, right? So to do that, we do using, and then we are gonna be needing an intersection type. Intersection. But we first need to create the fields. So we call field.of here, and we use the source mirror. So source mirrored lm labels, and then source mirrored lm types, right? Let's break the line here because I can't see anything. And now we just say, we just say that, and we do the same thing, but for the destination type. Mirrored lm labels, mirrored lm types, right? Yeah, cool. Let's format that, yeah. So this thing will actually, for us, will only work when the source has a superset of the destination fields, right? So if I go here and uncomment that, that should not compile, hopefully, please. Yeah, that doesn't compile. Perfect, perfect. That's just perfect, right? The error message is fun. But we can make it a little bit nicer by doing implicit not found, by using implicit not found. So if I just do, what was the, I think that was something like sources, fields are not a superset of destinations fields. Yeah, okay, hopefully it's less fun now. Oh yeah, look at that. Boom, perfect. Okay, so we've got a way of preventing building out something from that cannot be built out. So now onto the part where we actually build it out. Yeah. So first of all, we will be needing the values from the source, but as a map. So to do that, because source is a product, I can just do erase source. Yeah. Self is the source here, so self me product names. Yeah, that's right. We're gonna zip that together with the values. Product iterator, and just turn that into a map like that. Perfect. And that gives us a map of string to any, which is not the best kind of type I like to see here, but yeah, we're gonna do what we're gonna do. We don't use macros, right? Then we need the destinations labels to actually fetch those values from the source. So the labels like that. So we can just use const value tuple dest mirrored lm labels. Yep. And then we turn that into a list, and then we do the worst thing possible. We cast that to a list of string. It's possible to do that without a cast, but I don't really have time to explain it right now. But just, I pinky promise it's possible to do without a cast, right? Yeah, and that will give us the label of the destination type. So what we're left to do here is we need to fetch the values from the source, using the labels from the destination type in the same order, I should say, because the order matters when we construct that apparently. So let's go dest values, sure, and we just go dest labels map. So we got a label here, and we just like that, label. Boom. Okay, but that's actually just a list of any, and remember we want to actually return dest, right? So we have dest, the mirror of dest here, and we can use that to call from product on. So from product, as I said, that basically constructs the type, but we need a product, and a list is not really a product, so we can build out a tuple from an array. From array, yeah, perfect. Any. Nice. And then we just feed dest values, turn that into an array, like that. Boom, and it just works, right? Perfect. So I should be able to now run the if Metals thinks about that for a moment. If not, I can actually use my command line. It's really big. Wow. Scala CLI run. Okay, give a second. Come on. Perfect. Yeah. Oh, not cool. Okay, so I guess I need to do run main class. That's just awesome. Main class. Live basic test. Please work. Yeah, boom. See? It works. These hands are never wrong, basically. So yeah, the more detailed album got transformed into a least detailed album. There's even an assert here that we have the actual is expected, right? So I'm not lying to you that it actually works, and that still does not compile, hopefully. Right. Yeah, cool. Yeah. Okay. So that's the basic transformation done. Let's now move on to the more advanced ones. If I can find my mouse cursor, yeah. Cool, perfect. So intermediate ones. We've got two case classes again, track and a single. The only thing that differentiates them is instant and long. Sorry, the types that the timestamp is encoded as. The end product is just supposed to convert between them together, one way and the other way. That's because we'll be providing a type class that tells us how to map between an instant and a long and an instant. Yeah, so let's get right into it. I don't want a screenshot, thank you. I don't want this either. Come on. Yeah, intermediate. Okay, we're here. So once again, there's a small test that we'll be using later on. Okay, so first things first, I probably need to, why is not compiling? I know why. I probably need, oh my gosh. I probably need to, what do I need to do? Ah, yeah, I need to copy that because I'll be needing that in a moment. My hands are shaky and that does not help. Okay, yeah, perfect. So let's go to intermediate. Yeah, so that's the same example as we saw on the slide. And now for the implementation itself. So what we need to do is we need to go to the source type, fetch a name from that, look up the name of the field in the destination type, and summon a transformer. Sorry, I did not show what a transformer is actually. And summon a transformer, yeah, like that. And summon a transformer, so a type class that basically encapsulates transformations, right? From a source to the destination type. That only has a single method called transform. And I've provided only a single instance here, but we can provide any we want. That we only want work for identities now. Yeah. So how do we go from a source type, fetch the label, blah blah blah, and the way we're gonna do that is we go back to field, and we're gonna use another match type actually. So type. We're gonna call this fields name-wise, and it takes the source type, source fields, which is a tuple, and the destination fields, which is a tuple, right? And now for the fun part. So we will be going over destination fields, all of them actually. So let's first go through dest fields. Actually, I want to map over that. So tuple, that map, dest fields. Boom. We've got a here. I need to match over that to see if it's actually a field. So case, that's supposed to be a field. Case, field, label, and a type. Yeah. Cool. Okay, so yeah, I'm missing one thing here right now. Okay. So right now I'm gonna leave this blank. I'm just gonna leave this as nothing for now. If I can spell nothing. Yeah. Okay. And we're gonna need another helper match type that will actually, given a label, we want to feed it a name. So basically that match type will be called type of, right? We're gonna feed it a name of a field and a fields tuple. And what it's gonna do, it's gonna go recursively through the tuple of fields and try to find out what type lives under that given name in that tuple. So to do that, we will match over fields, right? Fields that match, boom. And in case we actually find our field, so it has a name that's basically the same type here. It has some type, and it probably has a tail because it's still a tuple. We just return the type here, so that's the happy path. But in case we don't find a match, and it's a head and a tail, we just recursively iterate over the tuple until we basically die. Oh yeah, the name, yeah. And you can see that I don't handle the empty tuple case here because I want the compiler to yell at me if it hits the empty tuple, because that means there's no name, sorry, there's no field with that name somewhere, right? Okay, so now that I have that, I can try doing transformer, because remember, we need transformers, right? So transformer, the first parameter is the source, the second one is the destination. So to get the source type, we do type of label and call that on source fields. Yep, like that. And remember, we are already mapping over the destination fields here. So the type here is actually the destination type. Type, like that, right? So that, if this actually reduces, that will give us a tuple of transformers for a given field, basically a field name, field-wise transformers, or whatever the name is. Okay, and now we are back here into our implementation. So the first thing I'm gonna do is I'm gonna create fields. So the field.of source mirrored lm labels, source mirrored lm types. Yep. And then the destination fields. Let's call it destination source fields. Yeah, like that. Field.of dest mirrored lm labels. Yep. Mirrored lm types. Yep. Okay, so we have that, and now we need to summon the transformers we need, right? So transformers. Let's summon our transformers. So we use summon all. Summon all. And we just call field that field name wise. Fields name wise. The name is trash. Sorry. Fields name wise, and we call that with the source fields. So literally just pass source fields and the destination fields. Here, don't want to do that. Okay, that leaves us with a pretty gnarly type, sure. So we just call it list, and then we cast it. So we know it's a list of transformers. Any. Okay, awesome. So it's a list of transformers. Yeah, and the rest of that is pretty much the same as we saw on the basic example. So destination labels, uppercase though. So const value tuple please, dest mirrored lm labels to list, and we cast list of string. Yep. We need the erased source, so that's self product element names, cool. Zip that with self product iterator. To map. Awesome. Okay, and the values themselves are pretty much the same. I messed up. I want to do that. Yeah. Just values. So remember that the transformers we summoned here actually in order of the destination field. So the field order actually is already alright. So if you just go to God damn it. Const. I already did that. Yeah, one more thing. Transform map. So we just need to get the transformers mapped to the proper field. So to do that, I get the labels, I zip them with the transformers, like that, and just call to map, which hopefully works. Transformers. Yeah. Yeah, that gives me that. Then I just, the last part of that is just going through labels, mapping over them, So we've got a label here. So transformer. We just call transformer map with that label. And then we get this source value, which is erased source with a label. Yeah. And then we just do the last thing. We transform the source into the value like that. And at the end of the day, we just do dest from product, tuple from array of any. This value, yeah, to array. Okay, hopefully that actually works. Yeah, so that's the whole implementation here. So we summoned the transformers. That's messed up because I'm not fields. Okay, yeah, that's better. Let's see the test, right? Okay, that doesn't compile. That's because, as you remember, we don't have a transformer that goes from a long to an instant or the other way around. So if I just do that, that should start working. I'll do actually that, not that, and do that. Okay, so the first one actually now works, right? Because that's now in implicit scope, and the second one also works. Let's run the test. Is there a cool little... No, there's not. What's the name of that weird class? Okay, just a moment. Okay. Intermediate test. Oh yeah, okay, that's okay, yeah. Okay, again. Like that, right? Yeah, so so that actually worked, thank God. And that's all there is to the the type class encoding of that. But we've still got one other one ahead of us, which is actually yeah, like that. How am I doing on time? Okay. So yeah, defense encoding. We are back to our original examples. There's the more detailed album. There's the album. It has additional 2 fields. So now what we want to do is be able to still convert from a detailed album to a slightly less detailed album, but also be able to somehow convert the album with lesser fields to the more detailed album, and that's by supplying configurations, right? So yeah, that's actually, I'm going to show you that in code, and that's not going to be live coding, but that's too much code for that. I'm just going to go through what happens there. Done. Fancy? Yeah. Okay. So first of all, now it looks. Yeah. So what the config options look like that. I'm supplying just a value of 9 for the number of tracks, just to show you that it doesn't compile if I don't do that. Yeah, just a moment. Spinning. Yeah. Okay. The error message is fun. I'm not gonna. Yeah, it doesn't compile. It's all that matters. I cannot misspell the field name if you're wondering. Yeah, that's still awesome. That doesn't compile, and the type is actually also needs to be set properly. Yeah, that doesn't compile. Awesome. So how it actually works? If I scroll up a bit, you'll see this fun thing. So it's a case class. It's called a builder. That has a whopping amount of, I believe it's 7 type parameters, yeah. And it basically encompasses the a builder of a transformation, sort of. So that's the source type, that's the destination type, that's the source fields. These are the fields that will be summoning a transformer for, and these are the fields that we've configured, and those 2 things we just need because reasons. so all of that is so this actually the source value is already in the builder, and the configs themselves are stored as a map of string to config, and config itself is just an enum of const on value or computed, where const you just feed it a value of something, and computed you can feed it a function that goes from the source type to the field type, right? And let's first look at the with field thingy and how it actually works. So if I scroll down, you can see that I call with field here, and I pick the field somehow, and I feed it a config somehow, right? And that needs to type check as well. So first part of that is the selector here. That's basically a function from a selector to the field. And what is actually a selector? So a selector is a selectable that is shown off before. And it encodes the fields as a named tuple of fields. So basically something like the name, yeah, it's called name, whatever, field name, maybe a string, and then we maybe have an age or whatever, field age, it's an int. Right. So it encodes like basically you get back a named tuple with the field names, but also the fields themselves inside, right? And that's how it works, because select dynamic then gives you the field name for free basically. And there's when you have selectables, there's like a synthesized cast inserted to the expected type. Afterwards. That's not visible here, that's why there's nothing here, literally nothing. But that type will actually be fixed to the proper type from that named tuple. Yeah, where am I? Here. So that's how the field names and the field types get resolved, and then you just feed it a config, right? And the implementation itself is pretty straightforward, because you just get a field. So I always have a selector here. That's why I need those dest names and dest types here. So I just get a field, and I just then copy the whole builder by putting the field name with the config inside the map. And there's one fun thing to that. So there's this with config thingy that is basically a type alias on that. And what it does is it copies over all of the types from here, right? With two changes. It removes one field from this, right? So we tell it to not try to summon a transformer for this field, and instead we put that field into the configured transformers field, configured field, not transformers field. Yeah, so that's how it works. That's how the types get more or less modified there. And now onto the transform function itself. So first of all, it starts off like the other ones. So we summon all of the transformers we need. But there's one thing that's different here. So instead of just a transformer, I use a field transformer, because I get the name of that for free here, right? So a field transformer is just a name of a field and a transformer. And to derive a field transformer, there's got to be a transformer for those two types, for source and dest. And the name, given that the name is a literal string, that can be just filled in by the compiler. So yeah, I get the field transformer for free, not really for free. But basically, I get the field and the transformer that it maps that maps to that field for free without doing any other stuff. So yeah, field transformers is just a map from string to transformer, just like we saw before. We grab the labels, we grab the values from the erased source, and now for the actually part where we transform that. So first of all, we go through all of the labels of the destination type. We try grabbing a transformer. If it's there, we apply it to the source under that label, because we know it's there, because otherwise it wouldn't compile. If it's not there, we are sure that it's in the configs, so we just grab that from the configs. We match on the config, we either return a value of that or just apply the function that's inside. And then we use dest from product, turn that into a tuple, we get a dest back. And is this fun thing still here? Yeah, let's run our test. Yeah, that works, yeah. But, give me a second, let's look at the code here. Okay, you're not cooperating. Come on. Not like that. Okay. Yeah. So just to once again prove to you that it doesn't compile if I do that. Actually, do what? Do that. I know there's lunch inbound. Just give me a second. Yeah, that doesn't compile, and we're free to fill in the blanks. Okay, so just the finishing touches, I guess. So yeah, a quick summary. I think using not going to macros can get us pretty far, and like pretty far. Like a lot of cool stuff can be done, and that was really just the tip of the iceberg, haha. But the crux of that is the error messages, which are pretty bad. They can be sort of kind of modified with implicit not found or maybe ambiguous implicit, right? But apart from that, they're pretty bad. But even if something doesn't really quite fit for us or the errors are too bad, we can still use macros, and macros can do everything. And the errors can be pretty nice, whatever. Macros are there to be used. There's no shame in using macros. Macros good, actually. So yeah. That's all. That's the repository with all of the code you saw here, and that's it. Yeah, that's it. Yeah.
Can you come back on what summon all is exactly doing?
Sorry?
The summon all function.
Which one? Sorry.
Summon all.
Oh yeah, summon all. Yeah.
What is it doing exactly on the other one?
Give me a second. Yeah, summon all. You feed it, imagine this is, let me step over that. Imagine this is not, instead of doing this, you just feed it a tuple of value 1, value 2, value 3. And that materializes all of the type classes that are like encoded as types here. It may fail at compile time if there's no instance for the type class, right?
Does summon all have to be inside an inline block?
Yeah. However, it can be top level, but the types need to be known, right? At the moment you invoke it, basically. Yeah.
I was wondering how that compiles.
Yeah. Seth?
You mentioned that you need macros to get good error messages.
Yeah.
Am I right that you would also need macros in order to get transformers that have good runtime performance?
Yes, yes, that's totally the truth here. That the runtime performance here is pretty bad probably because it's just a map lookup, right? I mean, map lookups are not that bad, but it's not a field access on the JVM. So yeah, there's no way of inlining a call to a case class that gets the field basically. Yeah, that's a good point. Actually, don't know. I haven't checked. The thing that I did there, it compiles under 5 seconds or 6 seconds, so it's not that bad, I think.
We all just saw Mateusz's talk yesterday, so we're
yeah, I know. Yeah. Anything else?
When would you choose a macro versus when would you choose a type level?
Well, that depends. Probably when you plan to have a library and maintain that library, you probably want your users to don't be bitten by the runtime performance of that, right? And the error messages and things like that. But I've been pretty successful with sticking with that on projects where I, for example, had to derive stuff like gen from Scala check, right? So that works pretty fine for tests, etc. And it probably works pretty fine for all the other type classes. Yeah, that's basically it. Anything else? Okay, in that case, thank you.